Welcome back to the third video of our review for the New York State Chemistry Regents. We're going to go through bonding and naming today in this video, and we're just going to hit on the main topics. It's not going to touch on everything, but it will incorporate all of the most important stuff from this unit. So let's get into it. First off, if we're going to talk bonding, we have to talk about why things bond. And the reason things bond is because there is an attraction of electrons between two atoms. And to explain that a little bit further, we use this saying that 8 is great, because the goal of every atom is to have a full valence shell. Sorry about that. Full valence shell. And that usually means 8. Sometimes it's 2. In the case of hydrogen, helium, lithium, and beryllium. But the goal is there's always an attraction of electrons because every atom is trying to achieve this octet, this full complete shell. There are different types of bonds. The first type of bond that we usually talk about are ionic bonds. And those will happen typically between metals and nonmetals. So something from the left side of the table typically bonds to something to the right side of the table. And there is a full transfer of electrons. Electrons get transferred from the metal to the nonmetal. And then there is a positive and a negative attraction. And this is what we call an ionic bond. You can see it right here in this picture. This one electron transfers to this one, completes a full octet, completes an inner smaller octet, and now this positive and this negative are attracted. So that's the first type of main bond. The second type of main bond would have to be a covalent bond. Now these are the type of things that can also be called molecular bonds. This is between two corresponding nonmetals. So two things from the right of the table sharing electrons. Sharing electrons. Just like so. Instead of each of these atoms donating or accepting an electron, these two atoms just kind of use their extra electron to overlap and join together. But again, it always has to do with electrons being attracted. We can take these covalent bonds and we can divide them into two smaller types. First one being nonpolar covalent bonds. This results in an even sharing of electrons. The reason that you get a nonpolar bond is the electronegativity difference for the regents is 0. Right? So what type of covalent bond is between H and H? It's a nonpolar covalent bond. Both atoms equally pull electrons, so we get an even sharing. This is different from a polar bond. If you remember, a polar bond is when we have an uneven sharing of electrons. And this happens because the electronegativity difference does not equal 0. So in a HCl bond, there is an uneven sharing of electrons in which one atom, chlorine, pulls the electrons more than the other. And the third big type of bond is metallic bonding. Metallic bonding really doesn't get talked about all that much, right? So metals have a thing called metallic bonding, which can really be described as having mobile electrons. And so the electrons in a sample of a metal, they are constantly moving between all of the nuclei, swirling around in basically a sea, allowing metals to be conductive. So those are the three types of bonds. We'll talk a little bit about their properties, or the ones that are most important or most commonly show up on the New York Regents. And the first one has to do with ionic substances. Now, ionic substances will conduct electricity as a liquid or if they are an aqueous solution, aka in water. Either one of those situations, ionic substances conduct electricity. And the reason has to do with their moving charges or their moving separated ions. And if you look at this picture, you see the positive and the negative are right next to each other, and they cancel each other out. But the moment this salt, this ionic compound, dissolves in water, the positive and the negative get separated. And with this great distance between them, electricity can be conducted. And that's why a solid brick of salt does not conduct, but a liquid or aqueous does. Great. The last most important part of this unit had to do with molecules. So this is similar to bonds, but it's just a little bit different in that we have whole polar molecules and we have non-polar molecules. And the way we tell the difference between the two has to do with symmetry. If something is polar, it's asymmetrical, meaning the molecule has divisions. It has positive ends to it, and those positive ends are completely separated from those negative ends. And it creates a whole molecule that has a bit of a negative side and a bit of a positive side, which is very different from a nonpolar molecule, because a nonpolar molecule is symmetrical. These symmetrical charges, these symmetrical shapes cancel out the positive and the negative, and therefore this whole molecule, even though the bonds have interactions going on, even though these bonds have negative sides and positive sides, the whole molecule does not behave in the same way as this molecule. And it all comes down to the symmetry of the shapes. So one of the things that we've said in my classes is SNAP. And SNAP stands for symmetrical things being nonpolar, asymmetrical things being polar. And it's just a quick way for you to, remember the definition of each type of molecule. Now, the last bit of naming of bonding had to do with how you name something. So the rules are very simple. Step one, we always name the metal first. So if we were going to do, let's say, for instance, iron and oxygen, and we'll do FeO. Right? If this was the molecular formula, the name of this would have to be iron first, oxide. This is step one. Now, that wouldn't be the full correct answer, and we'll have to look at the second step to understand why. But iron oxide is what we would use for that to start. Now, if the metal has more than one oxidation state, we're going to have to use Roman numerals for specific oxidation state identification. And so we started with iron oxide, but let's go back to our formula, which said FeO. Well, according to science, iron could be a +2, and it could be a +3. Those are the options that it can be. In this particular molecule, it is one of those specifically. And we would have to be able to figure that out by kind of looking over at the nonmetal it's bonded to. Now, the nonmetal of oxygen is a -2 oxidation state. And in this balanced chemical equation of 1 iron to 1 oxygen, the correct oxidation state would have to be +2 because they cancel each other out. So for a molecular formula of FeO, the iron specifically has a +2 oxidation state, changing the name of this molecule to iron 2 oxide. We are using the Roman numeral that corresponds to the actual number the oxidation state is. And lastly, we can talk polyatomic ions. For New York State reference table or exam, there is a reference table E. Reference table E will give you the names and the formulas for every single polyatomic ion you need to know. The one thing that's interesting about it is these are covalent bonds. This ion, this polyatomic ion, is put together with shared electrons. And so it's covalent. Covalent things are not charged, or covalent bonds are not charged. But this particular configuration, right, creates a covalently bonded molecule that has a charge and thus behaves like an ion. And so this positive ammonium can attract a negative chlorine and form a molecule of NH4Cl, where that NH4 is the ion, the polyatomic ion, holding it all together. So I hope that recap of bonding and naming helped, and I hope that you feel a little bit more refreshed on what we talked about way back at the beginning of the year. So thanks for watching. Catch you in the next video.